All right, during the last class, you guys worked on a worksheet where you were solving log equations using the properties of logs. So we're going to continue forward and talk about solving log and exponential equations using logarithms now that we've had a lot of practice with logarithms. So let's just go back kind of as a refresher. We have the following equation, 4 to the x minus 2 equals 64. And these were the types of exponential equations we were solving before. Because these are the most simple type, because you can look at this and say, all right, 4 and 64, I can write both of those numbers with the same base. So I can use a base of 4 and rewrite 64 as 4 cubed. And since both of these have the same base, 4 to the x minus 2 and 4 cubed, we know that the exponents have to be equal to each other. So we can pull those exponents out, set them equal to each other, and solve for x. Okay. What I would like you to do, and make sure you do throughout this whole time, currently right now my calculator on the computer is not working, but make sure you're checking your answers. So store your result for x into the calculator, store it for x, and plug it back into the original equation. So store 5 for x, and then plug in 4 to the x minus 2. Okay, so we're going to take 5 and store it for x, and then make sure you plug in, and that should equal 64. Okay, so now we're going to move on to a little bit more advanced exponential equations. Some of them where we will have to use logs and others where we will not. So here we have 4 to the x minus 2 to the x minus 12 equals 0. And I want you to look at this and think about how this kind of seems familiar-ish to you. We've worked with a lot of equations that look very similar to this. Not exactly like this, but it kind of resembles an a squared or an ax squared plus bx plus c kind of deal, where it has those 3 separate terms that we're adding together and setting equal to 0. All right, so let's think about what we've done in the past with this. We've tried to get it so that the bases are the same. So I know for sure that I can write 4 and 2 with the same base. So I'm going to rewrite 4 as 2 squared, and 2 already has that base. The problem is I can't write 12 with a base of 2, but I'm still kind of thinking about how it looks like an ax squared plus bx plus c sort of problem. And you'll notice, oops, I'm sorry, this should be an x. You'll notice now I do have a squared term here. I have 2 squared and 2 and negative 12. Well, remember, multiplication is commutative, so I can rewrite this as 2 to the x squared, because it will give me the same thing. When I raise a power to a power, I'm just multiplying those powers together. So now I kind of do have something squared minus something else minus 12 equals 0. So what have we done in the past when it looks similar to a quadratic, but it's not exactly a quadratic? What we've done in the past is use substitution. So I'm going to let a equal 2 to the x. So if I do that, then everywhere I have 2 to the x, I'm going to replace it with a. So I have a squared minus a minus 12 equals 0. So now I do have a quadratic that we can solve. This is factorable. A minus 4 times a plus 3 equals 0. A equals 4, and a equals negative 3. So now I'm going to need to take my 2 to the x, and plug that back in for a. So I have 2 to the x equals 4, and 2 to the x equals negative 3. So we already know here, 2 to the x, what am I going to raise 2 to get 4? So x equals 2. 2 to the x equals negative 3. What would I raise 2 to get negative 3? Well, there is no number, since my base is positive, there is no exponent that's going to give me a negative result. So that one's extraneous, so my only answer is x equals negative 2. So go ahead and plug that back into your calculator, or remember, we want to make sure that we get those correct, plug that into the calculator. So check your answer. Store 2 for x. And then we'll plug it into the exact equation. 4 to the x minus 2 to the x minus 12. And you want to make sure that is equal to 0. All right, so what if we have 2 to the x equals 5? What we used in the past was trying to get these so they're written with the same base. But in this case, we cannot rewrite 5 to be a base of 2, and we cannot rewrite 2 to be a base of 5. So there's a couple of things that we can do here. First thing, method 1. This is in exponential form. So let's try rewriting it in log form. Log base 2 of 5 is equal to x. So now I just need to figure out what log base 2 of 5 is. Some of your calculators, you can just do that. You can just plug that into your calculator. Some, you have to put it into a common log, so we're going to use the change of base. Log base 5 over log base 2, and then you can plug that into your calculator. So go ahead in your calculator, do log base 5, log base 10 of 5 divided by log base 10 of 2, and see what you get. You should get 2.322, and so on. To check your answer, when you have the answer in your calculator, just hit the store button without doing anything else. And what it will do is it should say answer stored for x. So it's going to take your exact answer and store it for x. Okay. Let's put this in a different color so we can know that this is how we check our work. So without doing anything in your calculator, just take that exact decimal that you got for x, hit the store button so that it will say answer stored for x. So that you want the exact decimal to be in there. Otherwise, it's going to be off if you put in the rounded answer. Then put in 2 to the x, and that should equal 5. Here's our second method. Please make sure you write down both methods, because this second method that we're going to use will sometimes be the only possible method to use. In this case, we have 2 possibilities, but sometimes this method too, you have to use. So we have 2 to the x equals 5. Now remember, we talked about the relationship between exponential equations and log equations. What is the relationship between exponential equations and log equations? They are inverses of each other. So just like I would say if I had 2x equals 10 and I wanted to solve for x, 2 times x, I would use the inverse of multiplication, which is division, to solve for x. Or let's say I had x plus 4 equals 12. X plus 4, if I'm trying to solve for x, the inverse of addition is subtraction. So I'd subtract 4 from both sides and get x equals 8. So when I have an exponential equation and I'm trying to solve for x, the inverse of exponential equations is logs. So what I'm going to do is I'm going to take the log of both sides. Now you can use the log of any base as long as it's the same on both sides. So just to keep it simple, we usually just take the common log of both sides. But you can take the natural log of both sides, you can take log base 2 of both sides, you can take log base 12 of both sides, okay? Whatever, as long as it's the same on both sides. But we're going to keep it simple and just do log base 10 of both sides. So now now that we've taken the log of both sides, what can we use to try and get that x by itself? Well, we can use the power rule. Now that I have a logarithm, I can use the power rule to bring my x down so it's no longer an exponent. So I have x times the log of 2 equals the log of 5. Now to get x by itself, I have x times the log of 2. So I'm going to divide by the log of 2 on both sides. And you get x equals 2.322, etc. And make sure, and then use the same method for checking your answer as we did over here. So those are the two different methods you could use to solve those. But remember, like I said, method 1 won't always be able to be used. Sometimes we would have to use method 2. For example, I have 3 to the x plus 1 equals 2 to the 2x minus 1. So in this case, it becomes more difficult to use method 1 that we talked about. So what we want to do is take the log of both sides. So I have an exponential equation, and the inverse of exponential equations is the log. So I can take the log of both sides. So now, since these are logs, I can use the power rule to bring my exponents down, and I no longer have a variable in my exponent. X plus 1 times log 3. It's very important that you put those exponents in parentheses to show that the exponent all goes together. If you had x plus 1 log of 3, that looks like only the 1 was the exponent and you're adding it to the x. So make sure when you bring an exponent down, you put those parentheses around the exponent. All right, so this one gets a little tricky, because I don't want to just divide by my log base 3. I'm trying to solve for x. I'm trying to get to my x, which is inside the parentheses. So let's go to the side here. Let's say I had 3 times x plus 1 equals 2 times 2x minus 1. How would you solve that equation? If that was the equation you were solving, you distribute your 3 and you distribute your 2 to get those x's out of the parentheses. We're going to do the same thing here. Log 3 is just a number. So I'm going to distribute that, distribute it. Log 2 is just a number. So we're going to distribute to get rid of the parentheses. So we're solving an equation just the same as we always would. So we have, let's do it this way, x times log of 3 plus 1 times log of 3 equals 2x times log of 2 minus 1 times log of 2. So we just distribute those logs. Okay. what are we solving for? So again, let's go back to our simpler equation. We're solving for x. We're trying to get x by itself. So in our simpler equation over here in the red, what would I do to try and solve for x? What would be my next step? Well, you would want to get all the x's on one side, and you would want to get all of the other numbers on the other side. So I'd have 5 equals x. So we want to do the same thing over here. We want to get all of our x's together on one side and everything that does not have an x together on the other side. So I'm going to subtract x log 3 from both sides here so that I get all my x's on the right side, which means I also want to add log 2 so I get everything that doesn't have an x on the left side. So I have log 3 plus log 2 on this side. These cancel out. These cancel out, so I'm left with 2x log 2 minus x log 3. All right, well, unfortunately in this situation that's different from our equation in the red over there is I cannot combine these two sides. These two sides are not like terms. So we have seen something like this before. Look at the right side. I'm trying to solve for x. How can I get my x out of there so that I can solve for it? Well, we can see that we have everything on the right side has an x in it because I did that on purpose. I got everything with an x on the right side and everything without an x on the left side. So since everything on the right has an x, I can factor out an x. Oops. So factor out an x from the right side, and now to get x by itself I can divide by all of this. Divide 2 log 2 minus log 3. So x is equal to log 3 plus log 2 divided by 2 log 2 minus log 3. Now when you put this in your calculator, make sure to put parentheses about both the numerator and the denominator. So go ahead and put that in your calculator. Log 3 plus log 2, make sure you have parentheses around that, divided by 2 log 2 minus log 3, and make sure you have parentheses around that. You should get about 6.228, so on. Make sure you check your answer. So leave your answer just the way it is at exact decimal. Hit store for x. So it takes your answer and stores for x. And then plug it into the original equation. 3 to the x plus 1 minus, or then make sure that equals 2 to the 2x minus 1. Okay, let's just do a couple more of each type of example. So our first one, we have the 9 to the x minus 3 to the x minus 6 equals 0. Now remember, this was one that kind of looks like ax squared plus bx plus c equals 0. Kind of looks like that. So we're going to manipulate it a little bit to get that to work for us. So First of all, I need to make sure that these first two numbers are written with the same base. So 3 squared to the x, because I can rewrite 9 as 3 squared. So both of those have the same base. That way I can use substitution to plug something in that will equal that same variable. All right, remember I can rearrange this. 3 to the x squared minus 3 to the x minus 6. So now that's what these first two terms have in common. The first two terms have a 3 to the x in common. So we're going to let a equal 3 to the x. So we get a squared minus a minus 6 equals 0. So now we have a factorable quadratic equation. Factors to a minus 3, a plus 2. So we get a is equal to 3 and a is equal to negative 2. So I will need to plug that back in. Plug my 3 to the x back in for a. So 3 to the x equals 3. So what am I going to raise 3 to get 3? 1. And I also have 3 to the x equals negative 2. But since my base is positive, there will be no exponent that I can raise it to and get a negative answer. So that's going to be extraneous. So my answer is x equals 1. Okay, here we have e to the x plus 3 equals pi to the x. Again, I have an exponential equation, and there's no way I'm going to be able to get these two sides to have the same base. So it's an exponential equation, so I'm going to use logs to solve this. So which logarithm do you think would make the most sense to take of both sides? Remember, we can take the log of any base as long as we're doing it to both sides. So since I already have an e in this equation, I'm going to go ahead and take the natural log of both sides. So now that I have this in log form, I can use the power rule to bring my x down, my exponents down in front. Remember, make sure if there's more than one thing in your exponent that you're putting parentheses around it. That is very important. Quick question, what is the natural log of e? Well, remember, the natural log means you have a base of e. So what exponent would I need to raise a base of e to get a result of e? That would be 1. So the natural log can be changed into 1. So now I just have x plus 3 equals x times the natural log of pi. So just like solving any equation, remember we're solving our equation for x. We're trying to figure out what x is. So I need to get all of the x's together on one side and anything that doesn't have an x on the other side. So let's subtract x natural log of pi from both sides so we can get all the x's to one side. And we'll subtract 3 because I want to get anything that does not have an x to the other side. So we're putting all the x's on the left side, and anything that doesn't have an x goes on the right side. So I have x minus x natural log of pi equals negative 3. So on the left side, I put everything that has an x on that side for a reason. Everything on that side has an x. So I can factor out an x. from both sides so that I can divide to get my x by itself. So x is equal to negative 3 divided by 1 minus the natural log of pi, which is about 20.728. Remember, with your exact decimal, store that for x, plug it into the very original equation to see if you got the right answer. Okay, so interact math. This is a required practice. You're going to go to chapter 4, section 6, and you need to do exercises 17, 21, and 25. So please do those in your notes, and I will check to make sure that you have each of those 3 problems done by the beginning of class. See you then.